I'm Connor, and I'll be talking about a framework for modeling temporal networks using scientific machine learning. This was done in conjunction with the University of, it should be Canterbury, and with the thanks to Buffalo and LC for transport funding. So the problem that we're trying to solve is that we have a series of observations of networks, and we want to predict the next one in the sequence. So these type of network problems pop up a lot in, for example, protein interactions, network ecology, social networks, as well as symptom interactions. And so we may want to model these with differential equations. That means that we can get samples at differing time steps, and we can also generate predictions at different time steps. And so it would be really nice, because it's difficult to model these discrete changes going from one edge to no edge at a single step. It'd be nice to have these in a continuous system that we can model that and then throw it back into an approximation of our network. Luckily, there is a way of doing this. We can use a singular value decomposition, which is a way of breaking down a matrix. So we go from our adjacency matrix to a continuous state by using the eigenvectors. Once we have the series of E's are in a continuous latent space, and we can use scientific machine learning to model their movement. From there, we can take a symbolic regression to find a kind of more robust predictor ahead of time. We've found that just using the neural networks from SciML doesn't seem to work very well. And then we construct a random dot product graph, which essentially says that the entries of the random dot product graph are the probabilities that there are an edge between two given nodes in our adjacency matrix. So we'll go into each of these in a little bit more depth. For our singular value decomposition, essentially what we do is we take our adjacency matrix, we can find a kind of arbitrary number of eigenvalues of that matrix or associated with that matrix. You'll see a little bit more in a second. And then in our case, we take 2. And from here, we can see that this row here, for example, is associated with this point here. And so if we were to take 3 singular values, 3 eigenvalues, we would be embedding in 3 dimensions and so on and so on. So one nice property that we get from a lot of these networks is that they are very kind of, they need very few eigenvalues to describe the system. So just some work on singular value decomposition. We get 2 matrices generally that we want to model, which is L and R. And these are associated with the eigenvectors of A transposed and A transposed A. So this means that we can work on non-square matrices. So if we have bipartite networks, for example, we can still use this system for them. Here we basically just truncate them. So we could take all of the eigenvalues and would get a very good estimate of our network. But if we just take the first few, we can still get quite a good approximation of the system. So notably, these embeddings aren't unique. They can be orthogonal rotations of each other. And so to model them from one time step to the next, we really want to make sure that they're aligned as well as possible. And so for this, and as well as working with DotProductGraphs, we've created this package, DotProductGraphs.jl. Still working on that one, so if anyone's keen to help out or look more into that, feel free to contact us. And then for more information on singular value decomposition is this reference here. To give a little bit of an interpretation of movement in this latent space, here are the associated embeddings with each of our networks. And we'll be focusing on these 4 nodes here just to get an idea of how things will move. So at the first time step, we go from here to here. And as things get closer together, which is to say that they have more neighbors in common, they move towards each other in the latent space. So if we look at these ones here, we see that nodes 2 and 3 actually move on top of each other from one time step to the next. And that's because they have the exact same neighbors. So they're, in a sense, interchangeable within the network. Going from 2 to 3, we also have nodes 1 and 4 moving on top of each other here, because again, they're essentially interchangeable in the network from that point. I'll skim pretty quickly over this slide just because I think most people are familiar with scientific machine learning, but essentially what we're trying to do is combine some amount of domain knowledge with a neural network to create a differential equation. For our proof of concept that we look at, we're focusing largely just on the neural network. Currently, we haven't actually applied it to any domains, but we wanted to know just how the neural network would perform by itself. For symbolic regression, we use symbolicregression.jl. We found that really helps to give a better prediction when predicting outside of the data, as you'll see in a little bit. And the idea is basically we can take our neural network, which we don't really have a good interpretation of, and we can move it into some set of known functions that we can interpret and understand a bit better. So the first system that we look at is this system here with 3 communities. So essentially we have 3 large clusters, and we focus on modeling just one node to kind of keep the problem size as small as possible. At each time step in this system, the edge with this node here is the one that we try and model, and it loses an edge with the community that has the fewest nodes in common with. So at the first time step, it'll lose this one here. At the second time step, it'll lose this one here, and at the third, it'll lose this one. Just a note, this is just a simplified representation. In the actual system, we're working with, I think, kind of tens of nodes for each of these bigger communities and many more edges just to generate a bit more data. When we run this whole process through for this system, we get this little animation here. So the green is the target node, which is where the node should be. The blue is the neural network prediction, and the orange is the symbolic regression prediction. So we see that when we're working outside of the trained data, so this is an ODE from starting from unknown data, the symbolic regression prediction works a lot better than the neural network. The neural network kind of very quickly veers away, whereas the symbolic regression moves a bit closer in the right direction. We haven't done any benchmarking because there's still a lot of optimization. We haven't looked at kind of optimum structures. This is really small scale proof of concept. The other system that I wanted to focus on is this long tail system. So in this, we wanted to look at this because the singular value decomposition really struggles to capture these kind of long tail structures. You need essentially the same number of singular values as there are nodes in this tail. So we wanted to see what happens there. In the system, all that happens is this target node moves one further down the chain at each time step. Again, this is a small representation. The system that we trained on is a lot bigger. And as we see, this here is the target node kind of jumping all over the place, but it really is not captured by either the symbolic regression or the neural network prediction at all. So there's still a fair bit of work to do to kind of optimize this type of stuff. And we hope that this kind of gives a little bit of an idea of what future work could be. In particular, we really want to focus on GPU compatibility. We want to increase the ability for people to choose their own eigenvector engines, as well as optimize neural network structures for predicting these type of systems, and start looking at applications where this could be used. Thank you very much. We wanted to be able to model continuously, just because it meant that, for example, if you're looking at ecological networks, it might not always be feasible to sample at a regular time interval. And so being able to do this, you can kind of more easily model it or get samples and predict at different time intervals.